Okay, I guess we'll begin. We've got a lot to get through today, so I'm just going to start lecturing right now. As you can tell, I'm not Hugo, but I will be your Hugo for the day. Hugo's in Japan, and he asked me to talk to you guys about discrete Fourier analysis for today. This is a field that at least initially came from theoretical computer science and sort of the study of true and false valued functions. But over the time, it's given applications to everything from social choice theory, which is a sub-branch of actual economics, to obviously statistical mechanics, which is why we're doing here, probability, geometry at some point. Maybe we'll get a small taste of that by the end of today. And the general perspective we're going to be taking is one of a very, very almost meaningless generality, because what we're going to be talking about today is functions who only have a discrete number of inputs. Pretty much that generality. So let's actually look at the objects we're talking about. So we consider omega to be the Hamming cube, n-dimensional Hamming cube, negative 1, 1 to the n, endowed with a uniform metric. Uniform measure, excuse me, I misspoke. Oh, just one thing. I know I tend to speak a bit quickly, and my handwriting is not that great, so if you don't understand either what's written or what's said, please stop me. I will repeat myself and take absolutely no offense. So when we say we endow with the uniform measure, we pick a point uniformly, and x will generally be a random variable which is valued at omega. Now, I'm going to work with the uniform measure pretty much throughout the day. But if I work with any product measure, that is any probability such that each bit, each one of the sort of coordinates I'm going to call a bit, again from the computer science perspective, each bit must be independent. But outside of that, we really have very little constraints. It could be 1/3, 2/3, anything. The only thing you have to be slightly careful is in the case if the product measure depends on n. That is, a probability of getting +1 is, let's say, 1/√n. Then nothing I'm saying is going to be correct. But as long as the probabilities stay constant and independent of n and bounded away from 0 and 1, everything I'm saying pretty much holds. But again, for the sake of this class, 1/2, 1/2. The probability of x equals xi, equals +1 is 1/2, independently for every coordinate. So consider we're going to consider L2 of omega, which of course the L2 condition is completely meaningless here because I only have finitely many inputs. Any fine function is L2 automatically. But I'm going to consider about L2 because I want to consider this as an inner product space and a normed space for that matter. So it's just a convenient notation. L2 of omega, of course, the space of F from omega to R. Now the important definition here is F is called Boolean. If its range is exactly the two values -1 or 1. Now this is sort of one of those definitions that's not 100% standard. You can say 0, 1, -1, 1. I'm going to stick with -1, 1. But you can generally think any value, any function that takes on exactly two values can be normalized to be a Boolean function. But the fact that this is exactly two values is going to be almost like basically the basis of the fact that we can come up with this theory. Because while L2 of omega is clearly a linear space, just take two functions we had, the space of Boolean functions is awful. There is no sort of nice involution on it. So we're going to just consider it instead of a subspace as a subset of L2 omega and see what we can say about general functions and about this subset that lives inside of L2 of omega, which is of course much smaller. It's in fact finite. Okay, so this is going to be the object we're talking about today. So we've got a linear space. The first thing we want to do is set some kind of basis which is going to be useful. Now of course, how many dimensions does L2 of omega have? as a real vector space? 2 to the power of n. We've got every coordinate can be whatever value we'd like, so it's a 2 to the n dimensional space. So I'd like to come up with a basis for that, a basis that's going to have some nice properties. So I define chi-s, this is going to be my basis vector, and it's going to be given by just the product of the coordinates in S. This is also frequently called the parity function on S because it just asks how many, do you have an even or odd number of -1s inside of S. Of course, for the empty set, we consider chi of the empty set is identically equal to 1. There are 2 to the n such vectors, so at least combinatorially, this could be a basis, and in fact it is. It actually forms an orthonormal basis with respect to omega. Of course, I didn't technically define the inner product, but I guess just to be safe. For 2 functions, we define the inner product exactly the way you think. By just summing the coordinates and averaging over the possibility of x, which is, of course, by definition of the random variable. The expected value of the product. Now you already see that why plus and minus 1 are going to play a funny role here, because if these only have plus or minus 1 values, things are going to be much, much nicer when we take inner products, right? Okay, so let's just prove this quick. All we will need to show is orthonormality, right? If I can show that this set is orthonormal, linear independence is for free, and given the number of vectors, spanning is for free as well. So it's sufficient to show that these guys are orthonormal. So if I multiply these two together, all I'm getting is the chi of their symmetric difference, right? Just consider all the elements. Anything that shows up twice gets squared. Square root of plus or minus 1 is always 1. So it's just equal and the expected value of each one of these guys is just 1. Obviously, if I take the empty set, that's the constant function, the expectation of a constant function, 1. And if there is any bit whatsoever, if there's any xi that survives, that is in there, by independence, the expectation factors and the expectation of each individual bit is 0, plus or minus 1. You'll notice here that if I were to move away from the uniform measure, that is, give a probability p to be plus 1 and 1 minus p to be minus 1, these chi-s's will not have 0 expectation. This would also mean they're not the correct Fourier basis. This is sort of the reason I picked this particular basis for this particular measure is this property, that they form an orthonormal basis. So as always, orthonormality depends on your measure. So watch out for that. Once we have this, these two facts together imply that if we just take the product, we just get a Kronecker delta function that fires whenever s is equal to s prime, and that's exactly orthonormality. So this basis is orthonormal with respect to my inner product, and everything is, by counting dimensions, it's spanning, and everything is good. I'm frequently going to call this the Fourier basis. So chi-s, I guess technically it's a Fourier-Walsh basis because it's finite. Basis And as such, by sort of notation, I define f hat of s by the expansion nothing too exciting here. This is pure definition. Of course, that also means that if you'd like to know a particular value, you can just consider the inner product of f with chi-s. Now, the fact that I'm calling this a Fourier Walsh basis is sort of suggestive, right? You might be thinking, where on earth is harmonic analysis coming in here? And there actually is a full harmonic theory behind here, which I'm hiding. This is omega negative 1, 1 to the n, the Hamming cube, is an abelian group. In fact, it's a very nice abelian group. And given that fact, we can consider its harmonic dual, consider the functions that map its multiplicative characters if you'd like. And if none of this is making any sense to you, don't worry. We don't actually need to know any of this today. But this is actually truly a Fourier basis in the standard sense. But for now, we can just consider this a priori as an expansion, which might have certain properties. But it's important to keep this in the back of your mind, because these Fourier coefficients are going to carry a lot of information about our function. In fact, going to be spending today and most likely next week, trying to sort of prod what information can we get from a function based on its Fourier expansion. That being said, this is not particularly straightforward. I can't tell you, oh, if I look at the Fourier coefficient associated with a set of 5 elements, I get blah. So there's a few things to keep in mind as to why this is useful. The first is both by analogy to real valued functions. When we take a Fourier transform, of a real valued function, that Fourier transform gives us information about the regularity of the function and sort of some of the properties it has in phase space, of course. And in addition, Fourier transforms and heat kernels really play well together. We sort of have an entire theory based on that fact. So in our case, regularity is a bit harder to think about because we're living in discrete space. Right? There isn't really a continuity and a differentiation to make sense of. We'll define some operators that do similar things, but there isn't a natural way to think about this. But what fs is telling you is sort of how complex is the function? How is sort of the dependency spread out? We'll see in a second that if x does not depend at all on a particular coordinate I, then its associated, any associated Fourier coefficient is going to be 0. That is, any set which includes I doesn't have a Fourier coefficient. And to see that fact, you can just sort of look back to this definition over here, which is if I consider inner product of f with a chi-s, which does not include I, the xi is going to factor out and give us 0 when we integrate. I'll do that computation in a second. The other thing is, since we don't have heat kernels, what we're going to have is random walks. We're going to have what are going to be called noise operators, which sort of take this Hamming cube, information on the Hamming cube, and move points a bit. And that's going to play very, very nicely with our Fourier coefficient and going to be a very important tool in proving the main theorems that we will probably not prove today, to be honest, but at least state. Okay, one thing that we really need to do, though, if I have Fourier coefficients, I better have Parseval and Kkl theorems, and we do. If I want an expected value of an inner product of two functions, I can just sum up its Fourier coefficients, and therefore I can also compute the L2 norms. Nothing too exciting. This is true for any orthonormal basis. But there is something in particular which is important about this second formula. Boolean functions have the world's simplest LQ norms. For a general Q, for that matter, because they only gave you plus or minus 1. You take the absolute value, you're going to get 1. You take whatever power and whatever square, it's always just going to be 1. So as long as f is Boolean, this identity holds, and many other identities are going to hold, in fact. This one is particularly nice because we're going to use it to create a probability measure, because this means that the squares of the Fourier coefficients somehow normalize properly. So I'm going to formalize this later, but if I pick S, the probability of picking S with this coefficient, the Fourier norm squared, I'll get a properly normalized random variable. Very, very important. Okay, just a few more definitions, and then I'll promise we'll do something with actual content. If it's monotone, if it's monotone in the sense we've been talking about throughout the semester, if you've got coordinatized domination, here you get coordinatized domination of the function itself. It's odd, excuse me. It's odd if we look at the opposite point in the Hamming cube and we get the opposite value. And it's symmetric. If I take any permutation in the symmetric group, sorry, let me write that slightly clearer. If I take any permutation of the n values and just shuffle the labels, this f of x of pi is just instead of x1, x2, I look at x pi of 1, x pi of 2, etc. Then the value of f does not depend on the order. I can completely reshuffle. This is an incredibly strong condition. If this is true, then f really only depends on the number of pluses and minuses you have, and nothing else.
Is it characteristic of Boolean functions or not? It characterize Boolean functions?
No, of course not. You can come up with, I mean, if this were true, then any function whose square would be 1 would be...
No, not any.
Sorry?
You have, of course, other functions which is 1.
With L2 norm of 1, but this, I mean, since this is the basis.
But with norm 1.
Yeah, exactly. Just consider, I mean, I can come up with arbitrary f prime of s's, f halt of s's. It's a very, very large dimensional space. Unfortunately, it'd be very, very nice if that were true, but not true. Okay, so symmetric functions really, this is, so you can think of this as sort of an n factorial different conditions on the functions, right? That's very, very strict condition. So we'd like to come up with something that actually, weakens this, but still gets us the idea that every coordinate plays the same way. This is the notion of transitive symmetric. That is, if I take any two coordinates, there exists some permutation which sends I to j and fixes the value of the function. The intuition behind this is that basically every vertex plays the same role, even though complete symmetry doesn't hold. So this is by far the weaker condition. You can think of this as sort of a quadratic condition. You only need the pairwise things to work as opposed to the entire symmetry group. Okay. I've talked a lot in generality. Let's actually get down to something meaningful and with a particular concrete example. Yes?
You have some larger definition of symmetry with lower bounds, for example. I mean,
I'm sorry?
Last week, Hugo was talking about equivalences. So if you have like upper bound, the difference of Gaussian differences after commutation, for example, is there any such definition of symmetry?
I'm not sure, because we really want, these definitely imply, if you have transitive symmetry, then all the influences are equal.
Yeah.
But if you want sort of something, if you want to say if influences are bounded away from one another, I'm not certain there's a good way to formulate that, because even if it's up to constants, if you think about it in the Fourier norms, up to constants is enough to break this kind of inequality very quickly. So you really are, like, if you push your spectrum left and right, you can do some pretty awful things in terms of control. I'm not aware of one. There might be one, might be some weaker notion which can say that these don't act exactly the same way, but they're not too awfully different from one another. I'm just not aware of one that's both correct and meaningful in the sense that you can use it to prove theorems. Sorry. All right. Let's just get some Boolean functions on the board. So the simplest ones, this nomenclature sometimes comes from social choice theory. So these are usually called the dictator functions. Seriously, this is the literature. As I said, this comes from the notion of social choice theory, where you have n inputs and you want to make a single decision from it. And the simplest way to make that decision is, of course, to just listen to one guy. Have one guy matter everything. So the dictator functions are exactly our first level for Fourier functions, excuse me. They're the chi-i's. They're chi-i of x is equal to xi. So just to go through the thing, they are monotone. They are odd. Are they symmetric? Obviously. The fact that a single guy matters more than everyone else is quite important. And they also have the world's simplest Fourier basis, because they are Fourier coefficients. They are Fourier basis themselves. Excuse me, I misspoke. Their Fourier expansion is exactly equal to 1 at this one and 0 everywhere else. Silly functions, but they'll be useful as examples in a second. Let's try to write something slightly more interesting. The and2 function. Again, and from the computer science version of 2 bits, and you need both of them to be on in order to actually get your output out. And you can think of this in terms of, let's say, if you have a population of n, and you listen to exactly 2 people, but both of them have to agree for the decision to pass. So if you're sort of kind, you can think of this as a population of 2 people that need to agree. If you're less kind, then you just want to consider it a population of n people. You ignore everybody but the 2 most important people, but they have to agree. Again, this one is monotone. It's symmetric if the population is 2 people. It's not symmetric otherwise. It's not odd, you'll notice. You can switch the 2 guys. If there's disagreement, you'll stay disagreeing. And I guess just for the sake of actually getting some exercise, let's actually compute the Fourier coefficients. There's only 4 of them. It's not that difficult. So N2 of the empty set. What is the Fourier coefficient associated with the empty set, by the way? This is the one that has a really nice interpretation. Well, the basis is 1. So if I look at the Fourier coefficient, that is, I take the inner product of a function with the constant function, what am I getting? Just the expectation, right? This is equal to, sorry, I guess this is the and function, which is equal to +1 with probability 1/4, -1 with probability 3/4, so it's -1/2. So if we look by symmetry, obviously the first and second are going to have the same. And again, as we mentioned, any s which includes a bit in 3, 4, 5, all the way to n, automatically 0. Just think of this kind of product. If I have an xi here, when I is different from 1 and 2, and x is independent of it, this expectation factors. And therefore, we've got expectation of xi, 0. So in this case, you can just sort of do this by head. If x1 is equal to -1, then this is tautologically equal to -1 as well. So we get a total contribution of +1, -1 times -1 with probability 1/2. Now if x1 is equal to +1, the and x is equally likely to be plus or -1, because it basically completely follows what the second guy is saying. So that contribution is 0, and this is equal to 1/2. You can just do this by, if that went a bit fast, just write down the 4 possibilities. Nothing too exciting. Finally, final guy, if both of these agree, if they're both +1 or -1, this term is exactly equal to +1, but and x, if you look at the 2 corners of the Hamming cube, it's plus here and it's minus here. So that cancels out, giving us 0 contribution. But if they're different, this is negative and this is negative, so they're always going to match. So if they're different, this gives you 1. If they're the same, this gives you 0. Probability of them being different is 1/2. The reason I'm doing this is because I don't know about you, but this is not obvious to me. Negative 1/2, 1/2, 1/2, 1/2 is not the obvious expansion of this function, even though it's very, very simple. So it's non-trivial, my point is. It's very, obviously, the more complicated the function is, the idea of doing it by hand becomes completely and utterly ridiculous. But this will have a payoff later, I promise. Since we are talking about social choice and we do live in our society, it seems like an important thing to talk about the most obvious form of social choice, majority. So the majority. So the majority gives you +1 if there's more pluses than minuses, and -1 otherwise, and of course we'd like n to be odd. So that we actually have a well-defined majority at all times. So, monotone? Odd? Yes. You switch everyone's votes, you go from a plus majority to a minus majority. Symmetric? Yes, fully symmetric. In fact, there is this wonderful theorem usually called May's theorem, which says this is in fact the only function which has all 3 properties. Which is one of those things that you look at the first time and you say that seems completely insane, like this is relatively weak. Symmetric is not weak. Symmetric is very, very strong. The idea being is that once you know it's symmetric, you know it only depends on the number of pluses. So once you know it's odd, you know that it has to be well balanced. So that those 2 facts together tell you it's the sign of some linear polynomial. You can prove that relatively straightforwardly. That is, it's a sign of a1 x1 plus a2 x2 for some real values x, ai, excuse me. And then by symmetry, all the ai's have to be equal. So by factoring out, you're seeing that you really are looking at the majority of the functions. So this function is actually genuinely important. It's going to be maximizers and examples for a lot of interesting things. So let's see if we can get, again, I'm not going to give you its complete spectrum, although this is calculable in this case, just a matter of combinatorics. But let's look at least about a few things about the spectrum. First of all, its spectrum lives completely on odd cardinality sets. The reason is that it's an odd function. Nice notation there. But if I consider a situation where S is, so I guess, So just as a proof of this, consider the Fourier coefficient. It's given by the expected value of the basis function and the function itself. And just pair x and negative x. This is even, so these two are equal. This is odd, so those two are opposite, and we get 0. Now, the rest of its spectrum is non-trivial and in fact has weight on every single one of the odd numbers. So let's just calculate one. So this is going to be, again, the expected value of x1 times mn of x. And by symmetry, this is just equal to the probability that I'm going to condition on x1 equals plus 1 and subtract the two possibilities. Technically, I need to do the same thing for -1, but you can see that that's just going to double it. So instead of putting a 1/2 and adding two terms that are equal, I'm just going to skip that step. Just a straightforward computation. Now, for mn to be larger than 1, given x1 is equal to plus 1, I'm going to look at this sum of all the guys has to be 0 or larger. When I say all the guys, I of course mean 2 through n. Sorry. So all the guys except 1 have to be 0, including 0, because then the tiebreaker guy would go plus all the way down. And for this to be true, it has to be strictly smaller than 0, that is -2 or smaller. So this is equal. This is from 2 to n, so there's an even number, so this actually makes sense. And again, by symmetry, everything cancels out except one term on the left-hand side, which doesn't. So this is exactly equal to the probability by symmetry. So the first Fourier coefficient is exactly equal to the probability that everyone else is at a complete deadlock.
What did you write under the expectation? Expectation of half?
This one?
Just the one up. Half.
Oh, this is the half cube. It's not. Because obviously I'm not summing up over all the x's because I'm taking x and negative x, so just consider a particular half of a cube. This we know how to compute, right? This is just the classic binomial coefficient problem. We need to have as many pluses and minuses, and this is the probability of event. There's exactly this many ways, and using this sort of standard, Stirling's asymptotics, we know that by Stirling's approximation, as n goes to infinity, this goes to exactly the constant square root of 2 pi over n, plus corrections that are order 1 to the n to the 3/2. Naturally. Now, there is something interesting about this formula, because if I sum up the squares of these guys over all possible values of 1, so 1, 2, 3, 4, the first values, I'm getting something which is normalizing to a constant. Constant smaller than 1, so we didn't break that. But we sort of do have a situation where if we think of this as the Fourier mass, the spectral mass, in terms of the sum of the quadratic guys, the first level contains a constant amount of mass. That is, of all the possible square coefficients, just the ones that have size 1, which are of course a tiny fraction of the possible sets, have almost all the mass in the sense of there's only a constant left. It's interesting. This is going to have ramifications later, and I sort of worked through this example because majority is important. It actually comes up as a maximizer in a bit. Finally, there is one example which has been sort of, I'm sure, in all of your minds, and that's Bernoulli percolation. If I just consider this as an abstract probability space, I'm just have a product measure. Each edge is probability 1/2 of being open and 1/2 of being closed. And I'm going to set xe to be +1 when the edge is open and -1 when it's closed. So any event of Bernoulli percolation, if I now look at the indicator of any event, that's going to be, well, it's not quite a Boolean function because indicators take on value 1 or 0. But so for any event, for any a, I guess I need 2 times the indicator of a minus 1 is a Boolean function. Of course, if that event is monotone in the usual sense, that function is monotone in the usual sense as well. And of course, I'm not going to tell you anything about its Fourier spectrum because, God, that's going to be very difficult. This is a very, very sophisticated dependency on the structure. We know that having some edges here and some edges here, sort of the geometric structure involved is very, very important to coming up with a function. But we do actually, it's surprisingly easy to make things transitive symmetric, which is a far weaker version of it, but it's not that. If we consider the event to be, let's say, the crossing of a square, not transitive symmetric, obviously. The edges in the boundary and the edges in the center play different roles. But if you instead think of it in a torus, that is a translation invariant set, you just want to say, take the square, sort of impose boundary conditions on it so that each point looks like any other point. That function ends up actually being transitive symmetric thanks to the translation invariance inherent in the system. So that just formalizes the idea that in a torus, every point looks like every other point, right? And crossing a torus is the same as doing it here as it is doing it sort of by taking any translation of it. So some of these properties are useful. Now the other thing is that if we can now get some kind of understanding of properties of monotone Boolean functions in general, that automatically transfers to Bernoulli percolation by just noticing that this is a Boolean function. So this is sort of, if you think of this in terms of a tool to use for percolation, this is the big motivation. That any general theorem we can prove passes to percolation automatically. Make sure to see if I forgot anything in there. Okay, how are we doing on time? Okay, I'll just get a few more definitions and then let you guys go on a quick break. So the main thing we're going to be studying about these Boolean functions is their influences. And influences are exactly what you think it is. It's pivotality for percolation. It's the idea of what's the probability that a single voter actually changes the outcome of an election. It's some way of actually understanding a big function by understanding its dependence on single coordinates at any given time. So formally speaking, I'm just going to look at the probability that f of x is not equal to f of x when I switch the ith bit. So everything's the same, but the ith bit switches. So if you'd like to think about it in terms of percolation, this is exactly the expectation of xi being pivotal for the event f, event given by f. That is, it needs to be -1 at one point and +1 at the other when I just switch that bit, turn an edge from on to off, or vice versa, of course. This doesn't need to be monotone, so it could be going, even I increase an edge, I could be losing f. Don't care. Now, to me, this is really a question of geometry. This is, I think, the easiest way to think of influence is to think a bit about the sets in the Hamming cube. So, run the f Boolean. Define I'm going to consider a sub f to be the subset of the Hamming cube for which f is equal to +1. See how good I am at drawing three-dimensional cubes on the board. Let's consider the majority on 3 as a function. So this is -1, -1, -1. This is adding 1 in this direction, adding 1 in this direction, and adding 1 in that direction. So for the majority function, I need to have at least 2 + 1 for the function of phi. So this point, and this point. These 4 points are sort of in my plus set, and the other points are in the minus set. Now, what this is probing is saying I'm going to now look at all the edges that go in a certain direction. Let's say the edges going in the right of all 4. How many of them have one endpoint in orange and one endpoint in blue? That is all that influence is saying. It's saying it's considering the boundary of the set in the Hamming cube. So in this case, obviously, these two are influential edges. They do change from -1 to +1. So obviously you need to have the other two being tied and you making the deciding vote. And here, +1 already won. Here, -1 already won. So your vote doesn't matter. So you can see that the influence for majority 3, the influence of any given bit, and again by symmetry, is 1/2. Exactly half of the edges. And we'll see in a second what happens in larger Hamming cubes. But I think this geometric picture gives a really important sort of other version of a lot of these influence things. This is a question about sets, subsets of the Hamming cube and their boundary. So I guess this also gives us one particularly obvious thing. Suppose I want to maximize influence of I in the sense that I want all of them to be large and in fact their sum to be maximal. What set should I pick? What function should I pick?
Parity?
Parity. The idea here, if you think about it in terms of the Hamming cube, it's very simple. You just want to make sure that every orange point only has blue neighbors, so that you just want to two-color the cube. So -1 + 1, -1 + 1, -1 + 1. And that's exactly what happens for the parity function, which says every single guy, you just change the bit. If he changes, it changes. So this is majority 3. I really want this to maximize. 3, 4. And I have a huge boundary. But of course I'm also cheating. Because the set AF equals this set right here is totally disconnected. Obviously, no two guys that are in the same set are neighbors. So one of the things you may ask is, if I demand that A of f is somehow connected, for example, let's say f being monotone, that's the natural thing to do here. What's the largest possible boundary I can have? What's the largest maximal influence we can have? So that actually is a non-trivial theorem. We'll prove it in a second. Just out of a question, does anyone guess the answer? It's only like 3 things it could be, right? I should only give you a few examples. It's majority, actually. Majority actually ends up being the overall maximizer of total influence for monotone functions. We'll prove that in a second. Before we do that, I just want to use this particular interpretation to prove our first bound. For Boolean functions, the influence is bounded above by variance. Now, if we think of sort of balanced functions, that is functions that have the same number of pluses and minuses on the Hamming cube, this is not surprising because the variance would be exactly equal to 1. So, probability is bounded by 1. But this becomes important if we ever think of, let's say, biased functions, functions where there is maybe only one orange vertex anywhere. Then you really want to make sure that even though you have very little pluses, you also have very little influence to match with it, so that variance is the proper scaling. And the proof is basically 2 lines. So consider the number of influential edges is strictly bounded above by the number of points you have that are either orange or blue, because each edge has one of each, right? So now if I divide by the total number of edges, there's 2 to the n minus 1 edges, and 2 to the n vertices. What I end up getting implies that the influence of I of f with the 2 being because there's 2 to the n vertices and 2 to the n minus 1 edges. Now, suppose that the minimizer is this, so the probability is strictly smaller than a half. Then the probability is strictly larger than a half. So I can say, just completely for free, because whichever one is smaller, the other one, 2 times the other one is bounded below by 1. And this is, of course, equal to the variance when f is Boolean. So that's sort of the first indication that variance is the thing we want to scale influence by. The second indication, at least to me, is not necessarily a theorem as much as a reason that influence matters to us, which is, of course, the notion of Russo's formula. Yes. So if I take f to be a Boolean and monotone function, the derivative in p is just equal to the sum of the influences, which I'm going to call capital I of f for total influence. The proof of this fact is exactly the same as in percolation. You just consider the grand coupling. And because the function is monotone, we know that changing a bit from minus to plus can only possibly increase. That's why there's only positive terms in the derivative. And if we consider this instead of a function of a Hamming cube, but a function of the true n-dimensional cube that fires at probability p at each one, and use that as a grand coupling to be able to move one p to another, and take the derivative by just taking limiting arguments of the probability that at p and p plus epsilon a function fires, exactly the influences come up for the same reason that pivotality comes up in percolation. Yes? Oh, that wasn't the question. Good. So, given this formula, it becomes, I guess Hugo's done this probably 3 times, But just to make it clear that this holds generality, if I now show, suppose that the influence is much larger than the variance, in the sense that the influence is bounded below by a variance times a function of n, which is going to infinity. Then if I divide through by variance here and integrate, and yes, I realize this is not particularly formal. I think you've done this computation before. I just wanted to show you that this really holds not just for percolation, but for monotone Boolean functions in general. All I did is I wrote the variance as, is 4 times probability of f equals plus 1 times probability of f equals minus 1, divided through, and what we get is exactly the derivative of the log of this function, straightforward computation. And on the right-hand side, we get something that's very, very large, which of course I need to integrate. So this is actually much larger than p prime minus p, because I integrated both sides. So as long as p prime minus p is larger, is 1 over, let's say, r of n, where r of n is that ratio, then we actually get a sharp threshold theorem. So it turns out that sharp threshold is not a percolation phenomenon at all. It is a general phenomenon of Boolean functions whose influence is much larger than their variance. And that's sort of the goal of, one of the 2 goals of a lot of these exercises, is to see under what are sufficient conditions to prove this fact. Because obviously it's not necessary, right? Not every monotone Boolean function has a sharp transition. Just consider the dictator function. Dictator function is asking exactly one guy what he thinks, and if I change p, the probability of that remains p. So I'm not going to make a small change and go from epsilon to 1 minus epsilon the way we'd like in the sharp threshold function picture, excuse me. So our goal, sort of the main punchline, the Kkl theorems, which I think Hugo stated, right? Okay, well, I'm going to state it again and probably prove it next week, is to give us a sufficient condition for this. Okay, I think this is the good time for a break. Okay, sorry for going a bit long in the break. We'll talk back in 15 minutes and actually prove some things. Let's begin and let's continue. So that was sort of the introductory part where I just threw a bunch of definitions at the board. Now let's start getting some more technical tools. So one of the first is that we consider now the operator di, which is a discrete partial derivative. Which is given, takes one function and gives you another. By the following incredibly clever construction. Shocking, I know. We evaluate the function with the ith coordinates plus 1. We evaluate the function with the last coordinate minus 1. That should be a minus 1, of course. Otherwise, no, the discrete derivative is always 0. It's just a flat 0 function. That's where of course. You want to see what happens when you just change one value at x. So note that di is linear. Take two functions, multiply functions, everything is a safe. It's a linear functional from L2 of omega to L2 of omega. In addition, if f is Boolean, then it can only take on three values, -1, 0, or 1. So it's not a Boolean function itself, unfortunately, but it's pretty close. Furthermore, if f is monotone, it's in fact only 0, 1, because you can't have -1. You can't have a negative derivative by just increasing coordinates for monotone functions. I guess I'll just start with the actual thing. This is for general f. Oh, I'm sorry, this is not correct. So derivatives have very, very nice Fourier representations. They are going to have the same Fourier coefficients, and we're going to move the sets such that if I is not in the set, it's 0, and if I is in the set, we multiply instead by chi s, but by chi s minus 1 coordinate, so that it doesn't depend on I. It's very good that this doesn't depend on I, right? Because there is no I dependence here, right? I set the 1 and a -1. So this function can't depend on I, and that's why you can only sum up over I. That's over sets that include I and then take them out. So this would be actually all S's. Right? Nothing particularly exciting. So now we only have to think about the excuse me, the derivatives of these sets. As I said, if you just consider chi s where it's not, I is not an s, just look at this formula. All these guys, we don't actually change any of them. So 0. And by direct computation, just consider I being in S. So we get all the guys except I times 1 minus all the guys except I times -1 divided by 2. The minuses cancel out, and we just get all the guys except I. No proof today is going to be longer than like 3 lines. Very, very straightforward, and all from defining everything correctly. So great, we have a very, very nice, Fourier representation, and that's going to give us our first 2 non-trivial theorems. So the influence, wow, this is the least straight writing I've seen in a while. I apologize for completely screwing that up. Let's try to actually write in a straight line. Still didn't manage to. Oh well. And this is for f Boolean. How to do this? Well, if f is Boolean, then the derivative is either -1, 0, or 1. And it's 0 whenever, for any x in which the ith coordinate is not influential, and it's plus or minus 1 when it is influential. Therefore, if I just square it, I'm going to get both of those negative ones to be 1, and this exactly fires whenever it's influential. So that identity, is a direct consequence of this fact. Now, because of its Fourier representation, which by our Parseval theorem why does I have to be an S? Because if I is not an S, we don't have any Fourier coefficients. Nice. Well, actually, summation is written like this. For monotone functions, however, we finally get a true interpretation of Fourier coefficients that are not empty. The the influence of I is just the Fourier coefficient associated with the set, the singleton I. And of course, you can sort of see this is not true for general functions by just considering the parity function. The parity function has exactly one Fourier coefficient on the set n. And this formula still works because for any I, you just get the entire weight, but this formula is definitely not going to work. And the proof is, again, comically easy. Monotone. It's a 0 or 1 function, and therefore for all x, the first and second powers are identical. So the expectation of a function is given by its Fourier coefficient involved with the empty set. But because of the formula right there, the one with the empty set is exactly the one that's with the singleton for the normal function. And again, lest you think these are actual trivialities, this actually gives us the fact that majority has maximal total influence. So this is the fact that, that as long as you're looking at monotone functions, so monotone sets, the largest possible boundary is given by exactly the corner of the Hamming cube, the half quadrant given by the sum of the coordinates being larger than 1. Of course, I do need n odd here, so that majority is well defined. So the total influence is equal to the sum of the first level Fourier coefficients by that theorem over there. Sum of influence. This is of course equal by the definition of the Fourier coefficients, right? Each one is multiplied by the dictator function xi and then summed up by linearity. Okay? Since f of x can only be plus or minus 1, the best thing this can be is exactly the absolute value of that thing. But this equality is achieved exactly when f of x is equal to the sine of that. Exactly majority. Told you, no proof is longer than 3 lines. But this is actually a very meaningful theorem because of the following fact. We know we can exactly compute the influence of the majority because we actually already computed the first Fourier coefficient of majority, right? So note that the total influence of majority n is equal to the sum from I equals 1 to n order square root of n. And in fact, we get the correct constant. I don't actually know any case where you really care about the correct constant, but it's nice. Have the actual correct constant up there. Now, therefore, let's consider the following situation. Consider percolation on an arbitrary graph with n edges. So let's say I have some rectangle. Let's say this is an m by n rectangle, and some completely awful arbitrary graph here. No constraints whatsoever on the nature of the graph. I'm just going to say it has n by m edges, just so that it's somehow twisting, almost without even any constraints about whether it's translation invariant or whatever. Just can imagine sort of taking a grid and shuffling its edges in an arbitrary way. Regardless of any event we look on this thing, so a crossing in vertically, horizontal, whatever way you want to do it, the expected number of pivotals cannot be larger than the square root of n times n. That's pretty surprising, especially if you think of this as being completely oblong. Then we know that if we sort of, any event whatsoever has this a priori upper bound on its influence. And I was talking to Vincent earlier today, and he actually managed to use this fact to prove that if you consider this graph to, let's say, be translation invariant, but no rotation, no anything, and you want to sort of ask, how do things degenerate in the sense that if we have a box propping property in a single way, how quickly is it possible for the length and the height to degenerate? It has to be at most polynomially. Because if this was somehow, it's exponential in n and you could still cross, you could manufacture lots and lots of pivotals and contradict this kind of bound. So even through this completely trivial bound, you can actually get non-trivial information about percolation on general graphs. And at least as far as, well, Vincent told me this and I trust him on this thing, if this is properly formulated, this is the only known proof of non-degeneration, of only polynomial degeneration of percolation on general graphs. Cool. There is one other consequence of this theorem, which I feel like I'd sort of be remiss not to mention, given the fact that we're currently standing in Geneva. I've heard this theorem being called Rousseau's theorem. Rousseau is in Jean-Jacques Rousseau. I'm not even kidding. There is a way to interpret this, which is this sum, for a general function, if you consider this as a voting scheme, is the expected number of people who agree with the final outcome.
Is it what?
The final outcome. So if you imagine you have a bunch of people voting, each one is equally likely to vote plus or minus, and F gives you the final outcome. And you ask, what is the expectation of the number of people who voted the same way as the final outcome? That's exactly given for even non-monotone functions by the sum of the first Fourier coefficients. You can just write that out. It's a very simple computation. And the fact that majority maximizes that is actually a statement that was first claimed in Rousseau's social contract in the sense of as an argument for democracy, because the important way is to make sure that as many people agree with the outcome as is humanly possible. Listen, how many times do you get to talk about Rousseau in a math talk? I figured it was worth mentioning. Okay. Our second non-trivial bound of the day. The Poincare bound. Whereas a single coordinate was bounded above by the variance, the total one is bounded below by the variance. So by just the representational formulas we have before, this is the sum, excuse me, the L1 norm, if you will, of this vector. And that's by the representation formula the sum over all coefficients squared over sets that include I. So if I reverse that sum, I note that every set is every I is included in a set exactly as many times as its cardinality. Right? Wrong way. By just a trivial bound, which is if I sum over all non-empty sets, this is at least 1. This is the expectation squared. This is the L2 norm exactly. So this is equal to the variance. The reason this is called a Poincare inequality is because this is somehow matching an L2 norm of the derivative, because we know that the influence is given by the derivative squared summed up. So this is an L2 norm of a derivative vector with the L2 norm of the usual function. This is exactly what Poincare inequalities do in real valued functions. So this is why it's considered a Poincare inequality. So I guess at this point, this would be a good time to actually formalize a thing I talked about before, because as you can see, these f hat squared sort of come up a lot. And this is, because it's a Boolean function, we can actually normalize a random variable which has that as its support. So let's be formal here. So I call script S of f the spectral sample of f, and it's a random variable that's supported on the power set of n. It's going to give us a subset of n, with the probability that S of f is equal to a particular S is exactly equal to the square of the Fourier coefficient associated with S. Because f is a Boolean function, we know that the sum of these normalized to 1, and this is a proper random variable. So in this terminology, we see that the total variance is exactly the expected value of the size of the spectral sample. This formula right here. And in fact, questions about the spectral sample are going to pop out left and right for the rest of the, well, really for the rest of the next 2 talks. Is Poincare tight? Is this inequality the best we could possibly hope for? I mean, you can sort of guess by the way I'm phrasing it that the answer is yes, but can anyone give me an example?
Dictatorship.
Yes. Well, there's one example that's actually a lot easier and stupid, which is the constant function. Right? The constant function, no one has any influence, but there's no variance either. But if you want something non-trivial, yes, the dictatorship functions. The variance is 1 minus the expected value. The expected value of dictatorship is 0, because a single guy is equally likely to go plus or minus. And the total influence, as we mentioned before, one guy has influence 1, all the rest of them have 0, so the total influence is 1. So dictatorship realizes the Poincare bound. So we can't really hope to do in general better. By the way, if we allow p to vary with n, Poincare stops being tight. That is, if we consider functions whose variance might move to the left and right and scale influence properly even, Poincare is not tight. You can get an improvement by a logarithmic factor, but for our case it is tight. By the way, another thing that to mention is that dictatorships and the constant functions are the only functions that realize Poincare. Every other Boolean function has this, does not realize this. And that's general theorem about functions whose Fourier weight is only on 0 and 1. Because as you can see from this, if the spectral sample has a positive probability of being larger than 2, larger than or equal to 2, this becomes not tight. And the only functions that have the property that S is supported on sets of size 0 or 1 are dictatorships and constants. It's not a hard theorem to prove. Let's now look at the maximum influence instead of the total influence. That is the largest guy of all the possibilities. This is Poincare. And this is our earlier proposition. Is this tight? Again, from above we know it's tight, we have dictatorships. Is this tight? Let's say, is this tight for, if you are worried about whether we can manufacture something awful, let's say Boolean and monotone. Maybe we can sort of manage to get a better non-trivial bound if you look at Boolean monotone functions. And now we seem to be a bit more in business, right? Because for Boolean functions, we already know what's the best possible influence, and we know that 1 over square root of n is at least achievable, which is much better than 1 over n. But we can't imagine that majority is really going to be the best thing here. We know the majority maximizes total influence. It'd be rather ridiculous if it also minimized the maximal influence of a single coordinate. That's in fact true. We can actually come up with a function which does much, much worse than majority in terms of the single influence, and it will be transitive symmetric and have all the nice properties we can hope for. And that is the tribes function. This is another one of those functions which comes up a lot because it provides a very useful example for many of questions that come in both theoretical computer science, social choice, and sometimes this. This is sort of the main thing we're going to talk about is the fact that it actually minimizes maximal influence over all possible, Boolean functions. So I'm going to take n, and I'm going to divide it into a bunch of sets, partition the function into sets of size log 2n minus log 2 of log 2 of n, because naturally. And whatever is left over, I'm just going to throw out and completely ignore for now. So if you'd like, you can imagine that n is a multiple of this. Or if you want to be careful about a few extra bits here and there, they're just irrelevant. T of x is equal to plus 1. Whenever at least one tribe is unanimous. And not minus 1 otherwise. So if all the tribes have at least one member who says no, tribes votes no. If there is one tribe which is unanimously yes, tribes votes yes. So you'll see why this weird normalization comes here, because we pick it sufficiently exactly so that tribes has constant variance. So with probability that tribe is equal to plus 1, actually let's do minus 1, I think minus 1 is easier. Probability that's equal to minus 1 requires all the tribes in all tribes one member votes no. And by independence, because there's n over k tribes, all of them have to vote no, and we need at least one to vote no in each one of them. Of course, by contraposition, this is 1 minus because this is the probability that all of them vote yes. Now this normalization is going to look normal. That's why the log 2's are flying around everywhere. But this is actually equality at this point. By definition, because 1 minus x is approximately e to the minus x, when x is very small. Cancel, cancel, these cancel perfectly, and we're getting something that's e to the minus 1, plus lower order. So that tells me that there's a constant probability of voting minus 1, and therefore a constant probability of voting 1. All of this implies variance is constant. it's independent of n. Now let's look at the influence of this guy. So I pick a particular coordinate and I ask for that coordinate to be influential. What does that mean? It means that in every other tribe there must have been at least one that vote no, and in my tribe everybody else has to vote yes. So the probability, the expected value of that, and the probability of that, and therefore the expectation of it being pivotal, and therefore the influence, is the same quantity over here except 1, times, inside my tribe, everybody has to vote yes. This is a constant, the same computation as we have here. Plus corrections of order 1 over n. Actually, probably much smaller. So since the variance is also a constant, what that tells us, so for tribes, we get that same 1 over n with an additional logarithmic term. The incredibly magical fact, which we're going to prove next week most likely, this is tight. This is the best possible lower bound that is possible. No function will do worse. And this is the theorem by Jeff Kahn, Gil Kalai, and Nati Lineal, one of Jerusalem, 2 out of Jerusalem, 1 of New Jersey, so hometown pride for me. There exists a universal path. So for some this is usually called the first Kkl theorem. The second one says something even more amazing, really. That the total influence is actually bounded below by the variance times the log of 1 over the maximal influence. Now, if f was a transitive symmetric function, this would be automatic. 1 implies 2 automatically for such functions by just summing up because all their influences are equal. But the fact that this actually holds for general functions gives us a really, really strange duality. Because what this tells us is if the maximal influence is small, that is, no particular coordinate has large weight to control, large weight in controlling the fate of the function, then the total influence must be large. And in fact, there is a partial converse, which is usually given the name of Friedrich's Hunter theorem, which says the following. If the total influence is bounded, then there exists a finite set of bits that almost completely determine the fate of the function, in the sense that if the influence is smaller than k, then there exists some function of k, number of bits, such that if all of those are plus 1, the probability that the function is minus 1 is 1 minus epsilon, is at most epsilon, excuse me. So Large influence, which is exactly the sharp threshold idea, is automatically given if you can just show that the maximal influence is small. And small influence implies that you really are ruled by finite number of coordinates and there's no chance you'll have a sharp threshold because a finite number of coordinates can go either way with constant probability. This is really, really sharp and gets you like rather amazing results. So it's now 11. Since we do have, I do have a tutorial, I'm actually hoping to lecture through the tutorial if everyone is okay with that. I guess I can give you another quick break and we'll pick up on here and talk. Definitely not going to get to the proof today, but at least I want to introduce the noise operator and noise sensitivity. That's the other major theorem that I'm hoping to prove next week. So I guess this week will be all introduction, just giving you all the concepts, and then next week will be a straight up proofs and some more technical results. So I guess I'll give you 10 minutes, 15 minutes? 10 minutes. Thanks, guys.